Welcome back to CET3136C. This is Logic Devices Programming, and in this video, we are going to discuss Chapter 7, which is Test Benches for Combinational Design. The learning objectives are that you will be able to explain the purpose of a test bench, summarize the steps for creating a test bench, and then to physically create a test bench for a combinational VHDL design. And we're going to spend the bulk of this video today typing up our first test bench for a half adder. First of all, what is a test bench and what is it used for? It's a VHDL program that impresses signals on a component and compares the output against known results for verification. So basically, a test bench is written to verify the design of a particular VHDL architecture. So part of the process for developing a component is to write a test bench for that component. The purpose of the test bench is to verify that that component does work as indicated. So for example, we're going to look at the code for a half adder, and we're going to write a test bench to verify that our code works. We use a test bench in conjunction with functional simulation and real-life testing on the breadboard to make sure that the component works as designed for every possible set of input combinations. So with a test bench, what we typically do is we call the piece of code we're testing a UUT, unit under test. So for example, today the half adder code we've previously written in other classes is going to be our UUT. Our test bench is going to be the stimulus generator, which generates inputs to the UUT, and then it monitors the responses of the outputs of the UUT. And it takes those outputs and it compares them to what the known outputs are supposed to be. If your test bench discovers that an output is not correct based upon a given specification, your test bench will give you an error, and then you can go and try to find the source of that error and fix your code. So for simple designs, like you've seen in the past, we can check the functionality manually by using the waveform generator. And that's great when you have a design with 2 or 3 or maybe 4 inputs, but what if you have a design with 50 inputs? What if you have a design with over 1,000 outputs? What if you're building a counter and you want to verify that the output of the counter is correct? And let's say that you have a mod 1,000 counter or something that counts to a very large number. You're not going to want to stare at a waveform to determine if every single one of those outputs is correct. So for more complex designs, the code and a test bench is what we use to check the outputs for every combination of inputs. And that's what we're going to be focusing on today in terms of learning how to write a test bench. So the steps for making a test bench, we start by determining the intent of the design from a specification. So for example, today would be what's the intent of a half adder? It has 2 inputs, it has 2 outputs, and it provides the binary sum and carry based upon the 2 inputs being added together. So that's our specification. Then you determine a strategy. How am I going to verify that the half adder works correctly? You have to determine the stimulus needed to achieve your desired verification. In our case, we need to make sure that we can simulate all 4 input scenarios for our 2 input half adder and verify that the outputs are correct for each set of inputs. Then you need to create a model that represents the intent of the design. The model is what we're going to be doing today. Create the stimulus generator, which means to simulate your model or run your model in a program. We're going to use Model Sim to run that program today, and then use the output of our test bench to evaluate the adequacy of our design. So one thing to keep in mind, test benches are usually not written by the same person who writes the architecture or who writes the design. So in this course, we are writing test benches to go with the code we've already written ourselves. But in a design world, you typically have a team of design engineers who will design the component, and then you have a testing team. The testing team had no hand in actually writing the code for a particular design or a component. Their job is to try to break your code as a designer. So if you're a test and verification engineer, you would be the person who looks at the specification for a half adder. You would say, oh, okay, it has to have 2 inputs, it has to have 2 outputs, and the outputs are going to be according to this truth table for a half adder. And then you would go and write a test bench for the half adder, not knowing how someone else on a different team might be writing the code to actually implement a half adder. And that way you actually have a second set of eyes on the project. If the person writing the code is also the person testing it, they may have some blind spots that they're just not aware of. So by having those two ideas, testing and design, separate, you actually are having a stronger method for verifying what you're building is actually going to work as designed. And with that, I'm going to hop over to Quartus and show you how to write a test bench for a half adder. So what I have open in Quartus is a previous project. This is the half adder project that was written a few weeks ago in a previous video. And I'm going to just go and open that exact project, and we're just going to add on to it. We're going to add a test bench onto what's already there. So open up that project, and then you're going to go to File, New, and you're going to add a new VHDL file to that project, and we're just going to name it Test Bench. And as I go through the steps for making the test bench, I'll explain how each step works. So we are going to begin with that library clause, our context clause with our library statement and our use clause. And then for the entity, it's completely blank. Test benches have a blank entity, so you'll have no port statement, nothing in there when you start writing your test bench. Next, we're going to design the architecture for the test bench. And just like any other architecture, you can give it whatever name you want. I'm calling my architecture behavior. It's going to be architecture behavior of test bench is. And then the next thing I'm going to do are create some stimulus signals. The stimulus signals are going to be the signals that send a stimulus or send a signal to our inputs. So since in my half adder my inputs are A and B, I'm going to call my stimulus signals A_TB for test bench and B_TB for test bench. Then I'm going to create some signals for the outputs. We call those observed signals. So I'm going to call those sum TB and carry out TB. And all of these signals are going to be of type standard logic, just like the signals they correspond to in the port statement for the half adder. Next, I'm going to begin my architecture. The first thing I have to add is what's called a UUT Port Map. This is where we connect our UUT, our unit under test, to this test bench code. In order to do that, I have to have this port map statement where I have the word entity, and then it's work, dot, and this right here must be the name, of your unit under test file. I called this half_adder, and that's what goes there. If you have a different file name, you want to make sure you type this in exactly as your file name on your half adder code. So next we have a port map statement. And inside the port map statement, I am going to send my stimulus signals and my observed signals in the exact same order that they are written in the port statement for the half adder. What I'm doing is I'm connecting this stimulus signal A_TB to signal A of the half adder, and so on. So I'm writing these in a specific order. They correspond with the order of the signals written in the port statement. That's important. So this is the beginning of my architecture where I connect the test bench I'm writing to the unit under test that I want all of my stimulus signals and my observed signals to connect to. Now that I have that UUT statement, The next thing I'm going to do is define a process to apply inputs. These are my stimulus inputs, and verify the result. Basically, I'm going to apply a stimulus, meaning I'm going to apply a value to A, TB, and B, TB. A, TB, and B, TB are like my signals A and B going into the half adder. Sum TB and carry out TB are like my outputs. I'm going to look at those outputs and I'm going to verify that they are correct based on the truth table for a half adder. So to begin, the first thing I need to do is begin my process. And I'm going to define a constant. My constant is called period. Period is going to be a unit of time, and I can define it to be 20 nanoseconds just like that. So this constant value is going to come up in a minute. I'll explain why we need it when we get there. Now I'm going to begin the architecture. The first thing I'm going to do is apply an input combination of 0, 0 and check the outputs. Here's how we do that. That's my input combination. I'm supplying an input for ATB and BTB, which are connected to signals A and B of my half adder. Then we're going to wait for period. So I'm waiting for 20 nanoseconds because outputs don't happen instantaneously. Inputs change, and then at some time later, even though it's a very, very small amount of time, it takes some amount of time for your output to be produced. So we're going to wait for 20 nanoseconds, and then we are going to check the outputs. Here's how we check the outputs. We use what's called an assert statement. This statement right here is going to look at sum underscore TB and verify that its value is 0. It's going to look at carry out TB and verify that its value is 0. If this entire statement after the word assert is not true, you're going to send a report to notify the user that there's an error. So with the assert statement, we check the outputs. If this is true, this line never gets executed. If this is false, that means that when the inputs were 0, 0, the outputs did not come out as expected or as dictated based on the specification of your design. And the whole purpose of a test bench is to identify those holes in the code. So then this report statement will send a message to you, the user, you, the person who's writing the test bench, to say, hey, test failed. In the real world, a test engineer would design the test bench, and if the test failed, they would simply send an email or they would document it in some way and send this code back to the design team and say, hey, your code didn't work for input combination 0, 0. Then the design team would go back into the code that they wrote, which would be the entity and the architecture itself, and they would look for logical errors as to why the test bench failed. A test bench is not a compiler. It's not looking for syntax errors. It's not looking for missing semicolons or incorrect data types. It is looking to see if the logic of the code that was written in this architecture does not hold up to a standard. So if the test bench identifies that there is an error, the code has to be rewritten or examined for a logical error within the architecture itself. So this is what we're going to do for each combination of inputs. So I'm going to basically copy and paste and update this for each combination of inputs. So when the inputs are 0, 1, the outputs should be a 1 for sum and a 0 for carry. If the inputs are 1, 0, the outputs won't change. Should still be a 1 for sum and a 0 for carry. And we're going to check combination 1, 1. So the outputs I'm expecting to get are purely based on the design specification. How is this supposed to work? So we're applying inputs, checking the output. As a tester, that's all you're doing. As a tester, you have no idea what's going on inside. All you're looking for is that when I apply a certain set of inputs, I get the output that was expected based upon the design specification. That's the whole purpose of a test bench. So here's our test bench, checking each combination from 0, 0 to 0, 1 to 1, 0 to 1, 1. Once we've checked every single combination, the next thing that we're going to do is indefinitely suspend the process. If we don't indefinitely suspend the process by saying wait with no condition, that means wait forever, this will check each set of input combinations, report back if there's an error, and then continue checking forever. We don't need to continue checking forever. We only need to check each one of these scenarios once to determine if there is an error. So indefinitely suspending the process stops your test bench from running forever. Otherwise, without this statement, it would continue to check and continue to check and continue to check without stopping. So we suspend the process. And that's the end of our test bench. That's the end of our code. So we're going to go ahead and compile by going to create update symbol files. It's actually going to compile every VHDL file in your project. So it's compiling both of these at the same time. No errors, no warnings. And now we're going to open up ModelSim. ModelSim is a software that we're going to use to actually run this test bench and see if there are any errors. The easiest way to navigate to ModelSim is to go to your File Explorer, go to the C drive, look for the Intel FPGA Lite folder, go into folder 18.1, go into folder ModelSim_ASC, and then Win32ALOEM, and double click this icon right here. That is how you're going to launch ModelSim. And it might look something like this when you open it. I am going to go to File and New and start a new project. Whoops, I have a simulation in process, so I'm going to stop that. I'm going to go to New Project. There we go. Close the current project. Yes. Okay. So I'm going to go and start a brand new project. I'm going to call it testbench_half_adder. You want to make sure that this is saved in the project location where all of your other files for this project are currently saved. So wherever you already have saved the files, so in this case, I have a folder for the half adder test bench, and I'm saving my work right here, and hit OK. Then you're going to add an existing file, so you're going to navigate to the half adder and test bench files. You're going to add both of them. So add both of them to the project by clicking open and then hit OK. And then hit close. You're going to compile each one of these files. You want to make sure you've already compiled them in Quartus, but you have to recompile them in Multisim as well. So you're going to right click on the half adder code, go to compile, and click compile selected. At the bottom, you should see a message that it was successful. Then you're going to compile the test bench file. At the bottom, you should see a message that it was successful. So after we have compiled our files, you're going to go to Library. And you should have a Work tab right here that you can expand. Once you expand that work tab, you should see both of your file names right here. You're going to double click on the one that says test bench. You're going to give it a minute because it's going to go kind of crazy. And when you look at your screen, you should see some different windows here. In the objects window, you should see the names of your signals. You should have the option to have a wave window right here. If you don't, go to view wave to turn that on. You should have a processes window, and there's a transcript down here. You're going to want to be able to view the transcript window as well. If you don't see transcript, go to view transcript and turn it on. So once we do that, we're going to go to start simulation. And this drop down right here. Again, select your test bench and hit OK. It's going to go crazy for a second time, then it'll reload, and then you're going to go back to your wave. Notice, as a side note, your code for the test bench is right here. You can read it. You can even edit it right here. If you do edit your code or make changes in any way, you have to recompile before you start a new simulation. But just so you know, yep, that is your code, and you can edit it right there. We're going to go to the wave window, and we're going to click and drag each one of our signals that we created within the test bench right here. Turn the transcript on so that you can see any messages. If there's an error, those report statements that we put in the test bench will send that message right here to the screen. This is how you'll know if it failed. So now that we have our waveform set up, we've got our signals, we're going to go to simulate, run all. If you were going to get an error, you would see it right here. It ran the test bench and there were no errors indicated. This is blank, so there were no errors with the test bench. Also, let's look at the waveform. So I'm going to pop this out. And this is the waveform. You can't see all of it right now, so you're going to right click and do zoom full. This is ATB, BTB, sum, and carry out. So we can see here via the waveform how the half adder UUT is responding to the stimulus. So the stimulus was ATB and BTB. Our observed signals were connected to the outputs, and we can see that it's working the way it should be. I'm going to pop that waveform back into the window. Again, if you were to get an error, you would see it right here. That's how a test bench works. Now what we're going to do is break the code so that you can see what it would look like if there were to be an error. So go back to Quartus, go back to your half adder file, and we're going to intentionally mess up the logic. So I'm randomly going to say, instead of carry out being A and B, let's say it's A, X, or B. We know that's wrong. But let's say as a designer, I had the wrong truth table or I implemented something the wrong way and I didn't realize it. The tester is the person who would catch this by writing a test bench. So I'm going to make that small change to my half adder code. I'm going to save it in Quartus and then go back to Model Sim. Go ahead and click End Simulation. Go back to the project window, and now you'll see that the half adder is no longer compiled. There's a blue question mark right here. It's connected to the Quartus, the files you have open in Quartus. So if you change something in Quartus, it can see it here. Anytime you change something, you need to recompile it. So we're going to recompile half adder. I don't have to recompile test bench because it's got a green check. It has not been changed. And now we're going to repeat those same steps. So double clicking on the test bench word within work and starting a new simulation where we drop down, click test bench here. We're going to let it set up. Okay. You can add these signals to the waveform if you want to. We don't really need to for this step, but I'll just go ahead and add them. And now we're going to look at the transcript when we run this. So go to simulate, run all. Here's our error messages. Error, test failed for input combination 0-1. Test failed for input combination 1-0. And test failed for input combination 1-1. So we know that 3 out of the 4 input combinations did not pass the test. At this point, if you're the person who wrote the architecture, you got to go back and figure out what's wrong with your logic. Obviously, we know what's wrong with it because we just intentionally broke it, but if your test bench doesn't pass, you'd have to go back and figure out why. And so that would be the job of the designer, to go back and figure out why. It's the job of the tester to thoroughly test the component to the best of their ability, to check every possible input combination, to make sure that the assert statements have the right output values. Because as a tester, I could easily misunderstand how a half adder is supposed to work, and I could have the wrong values here for assert. If I have the wrong values here for assert, it's not the half adder that's broken, it's my test bench that doesn't work. So as a tester, you have to make sure you completely understand what the output is supposed to be, and that's usually given in a design specification. That's usually not something you have to figure out on your own. You just have to make sure that design specification is interpreted correctly within your test bench. So to wrap up what we just did, this was our test bench. The unit under test was the half adder, with the signals A, B as inputs and sum and carry out as outputs. Our stimulus generator generated these signals A underscore TB and B underscore TB, which sent zeros and ones into the unit under test. Our signals that we observed were sum underscore TB and carry out underscore TB, which were connected to sum and carry out of the unit under test. And our response monitor is that assert and report statement that basically looks at the values of sum TB and carry out TB and decides whether those values are correct, and then sends you an error when they're not correct. So this is just an introduction to test benches. This is a very simple test bench for a very simple component. As you can imagine, test benches can become increasingly more complex. Again, think about testing a counter, which is something you will have to do in a future lab. For lab 6, you will have to develop a test bench, and you will have to consider a large number of inputs when you develop that test bench. So you will have to implement the idea of looping into your test bench. There are some practice problems posted on Canvas that include test benches where you have to implement a loop, so you can look at those for examples. And we will have another discussion on test benches for sequential systems later in the semester, where we will look at how a test bench will change when we have something like a counter with flip-flops involved. How do you test something like that? So this test bench logic is for combinational designs. So something with a straightforward data flow design is going to have a test bench that's set up pretty similar to the one that I've showed you here, where you're just basically walking through a truth table and testing various input combinations. You know, this is basically what we did here with the code. We walked through the truth table, looked at every single output. For a combinational design with a small number of inputs, that's what your test bench will look like. As we go forward, we'll talk about how to develop more complex test benches for more complex pieces of code. And that is the end of this introductory video for test benches.